Oh, it's so hot outside. Oh, perfect. A can of soda. Oh my god, it's so warm. What could I do?
An exothermic reaction is a reaction in which the system releases heat energy, which causes the temperature of the surrounding to increase. This type of reaction occurs when the energy used to break the bonds in the reactants is less than the energy released when new bonds are made in products. The extra energy is given off as heat. An endothermic reaction is when a system absorbs energy from the surrounding, usually heat energy. This in turn causes the surroundings to cool down. This reaction occurs when the energy used to break the bonds in the reactants is greater than the energy released when the bonds are formed in the product. This means that overall the reaction takes in energy. When ammonium chloride is added to water, an endothermic reaction occurs. Heat energy is absorbed and the temperature of the surroundings decreases. Thermodynamics is the study of relationships between heat and other forms of energy. The first law of thermodynamics states that heat is a form of energy and energy cannot be created or destroyed. Energy is transferred from one location to another and converted to and from other forms of energy. The location being focused on is the system. There are three types of system. An open system freely exchanges energy and matter with its surroundings. A closed system exchanges energy but not matter with its surroundings, and an isolated system does not exchange energy or matter with its surroundings. However, perfectly isolated systems cannot exist. The purpose of this experiment was to determine the amount of ammonium chloride needed to lower the temperature of a drink of 100 milliliters of water by 5 degrees.
In our can design, the drink is in a compartment surrounded by a second compartment filled with water. Attached to this is a third compartment containing the ammonium chloride. A button would be pressed, removing the barrier between the ammonium chloride and the water, beginning the reaction. The drinker would be told to gently shake the can to mix the two reactants, starting the endothermic reaction. In our design, the drink is surrounded by the solution so that the largest possible surface area of the solution is in contact with the drink. A large area of contact increases the rate of heat transfer, cooling the drink more quickly. The outside of the can would also be insulated to prevent outer heat from warming the drink. We used calculations to estimate the amounts of ammonium chloride and water needed to cool the drink. First, we calculated the amount of energy needed to cool the drink by 5 degrees. We then used the enthalpy of solution for ammonium chloride to find the number of moles of ammonium chloride needed. Using molar mass, we found the mass needed to be 7.59 grams. Then, using the solubility of ammonium chloride, we found we need at least 20.4 grams or 20.4 milliliters of water. These calculations were only theoretical, and we knew we'd probably need more ammonium chloride. The materials we used were a 222 milliliter pop can, a 400 milliliter beaker, water, ammonium chloride, a temperature probe, and a pipette. First, the can was filled with 100 milliliters of water. Second, 75 milliliters of water was poured into the beaker. According to our calculations, this amount of water was greatly in excess for the amount needed to react with the ammonium chloride. This amount was selected because this amount of water in the beaker approximately covered the area of the can containing the 100 milliliters of drink to be cooled. This larger amount of water increased the surface area where the water and the solution were touching the can, increasing the rate of heat transfer. Third, the temperature probe was placed in the can. Fourth, the can was placed in the beaker. This is to mimic our design of the drink surrounded by the solution. Fifth, once the temperature had stabilized, recording began. Sixth, 25 seconds after the recording began, the amount of ammonium chloride being tested was added. Seventh, the pipette was used to mix the ammonium chloride with the water and wash down ammonium chloride that stuck to the side of the can for a total of 55 seconds, 80 seconds after the experiment began. In the actual can, consumers would be instructed to press a button to release the ammonium chloride before gently shaking the can for approximately 60 seconds. This step simulates a gentle shaking. Shaking the can speeds up the rate of reaction by increasing collisions. Finally, temperature was recorded until 325 seconds from the start of the experiment, or 5 minutes after the ammonium chloride was added.
This is a table showing the temperature change for the amount of ammonium chloride used. As more ammonium chloride was added, the final temperature decreased. This is a temperature graph when 10 grams of ammonium chloride was added. As you can see, the temperature decreased by 3.4 degrees Celsius by the end of the 5-minute period. This is a temperature graph when 20 grams of ammonium chloride was added. The temperature dropped by 5 degrees Celsius within the first 75 seconds of adding the ammonium chloride, and continued to drop until the final temperature change was 6.3 degrees Celsius. This is a temperature graph when 15 grams of ammonium chloride was added to the water. The initial temperature of the water was stable at 21.1 degrees Celsius. After adding the ammonium chloride, the temperature decreased, and after 5 minutes the temperature had dropped by exactly 5 degrees Celsius. This scatter plot displays the change in temperature versus the amount of ammonium chloride that was used for all of our tests. As you can see, there is an evident linear trend of a larger temperature change as the amount of ammonium chloride is increased.
The rate of reaction is the speed at which a reaction occurs. A higher rate means a faster reaction. Several factors affect the rate of reaction, including concentration. Higher concentration leads to more collisions in a specific time period, which gives molecules a greater chance of colliding with correct orientation and successfully reacting. The graph comparing the amount of ammonium chloride to temperature change is a linear relation. This indicates that the experiment conducted is a first-order reaction. This means the rate of reaction is directly proportional to the concentration of ammonium chloride. We will now discuss experimental errors. We stirred the solution by hand, which meant stirring was inconsistent between different tests. If a machine stirred the solution, the stirring would be more consistent. Additionally, particles may have been stuck to the pipette used for stirring, thus changing the amount of particles in the solution. To fix this, the pipette could be carefully cleaned. The different starting water temperatures may alter the heat exchange, also causing error. Ensuring initial water temperatures were consistent would eliminate this issue. There are several differences in the design of our can and the experiment conducted, which would alter the amount of ammonium chloride needed. The can was stirred instead of being shook, and the container was an open system even though the real design would be closed. To more accurately determine the amount of ammonium chloride needed, further testing with a more accurate model would need to be conducted.